Okay, our class for today is on RC transients, resistor, capacitor, and transient just means a short period of time over which change is occurring in these circuits. Kirchhoff's law is going to apply to this circuit, and current we know is going to flow out of the positive terminal of the power supply and arrive at this plate. Now, no charge is going to flow through the gap, but current will be arriving at the plate and current will be leaving the bottom plate. So if you covered this up with your hand, you would say that it was just a piece of wire underneath. So an uncharged capacitor conducts, i.e. it looks just like a wire. So at the time zero, this is the time zero behavior, with the capacitor initially uncharged, then you're just going to have an initial current of V over R, that's 20 volts over 50 ohms. That's just 0.4 amperes of initial current. Now, there will be no charge on the capacitor at the beginning, and there will be no capacitor voltage. All of the voltage will be lost across the resistor. So the resistor voltage will be 20 volts. Now, after a long time, of course, this capacitor will charge up. Charge will spread out over the plates. There will be, if you like, a push from the positive terminal of the cell tending to push positive charges in this direction, but there'll be a balancing push from this charge buildup on this plate, and current flow will cease. So after a long time, the capacitor will be charged, we'll say infinity. Practically, it's a lot shorter than that. The current will go then to zero. The charge on the capacitor, we'll come back to that one in a second. We need to realize that with no current flow, all of that 20 volts is now lost across the capacitor. There is no voltage drop across the resistor. So Kirchhoff's voltage law continues to be true. So there must be a 20 volt drop here. Since capacitance is charge stored for a given voltage, we can find the charge in the capacitor then by multiplying capacitance and voltage. It was a huge 0.2 farad capacitor charged up to 20 volts, and so we've got a massive 4 coulombs of charge build up on that capacitor. So this is a little different in that this capacitor is initially charged up. We see there's 10 microcoulombs on this 2 microfarad capacitor. So what's going to happen in this case? Well, a charged capacitor is going to provide some charge flow through this resistor. It's going to act like a cell. So as we set up here in the small print, a charged capacitor acts like a rapidly depleting cell. So we just need to find the voltage of this. Since capacitance is charge stored for a given voltage, we can find the voltage here as the ratio of the charge stored over the capacitance. So we had 10 microcoulombs of stored charge on a 2 microfarad capacitor. The micro just cancels. So this capacitor, this charge capacitor, will act like a 5 volt cell. And that means that initially, anyway, we're going to have just a simple gray 10 circuit with 5 volts of potential across a 10 ohm resistor. So we'll just get a ½ amp of current flow. Now that is the time zero current. The current will quite quickly drop down to zero. So we say time infinity. In practice, it's a lot less. The current will decrease to zero. Here, by the Kirchhoff law, the resistor voltage and capacitor voltage have to be the same. So initially, there's 5 volts lost across the resistor, and the capacitor is providing the 5 volts of potential difference. Now, after a long time, the capacitor is totally discharged. There's no more charge. There's no more potential difference, no more current. So therefore, there's no more resistor voltage. Here's an example where we can get a little bit tricky then next. So here you see there's actually a couple of paths for current to follow. So we need to think carefully here. So we've got a cell here providing current. This capacitor is initially uncharged. So what's going to happen initially is current's going to flow from this cell, and then right here, because this capacitor is uncharged, this just acts like a wire. And so current will take the path of least resistance, and all the current will flow this way at time 0. And so, very simply, we've just got 30 volts over 10 ohms. And I should have moved this over a little bit. Running out of room here, so there'll be 3 amps of initial current there. Here, I can do this. You might have to erase and rewrite there. That looks better. Now, I'll switch colors, because what's going to happen at time infinity is that this capacitor is going to be totally charged up, but there's still a path for current to follow through this 5 ohm resistor. So I'll say I infinity in a different color goes this way. So now, how much current flow do we have there? Well, now that 30 volt drop is across 10 and 5 in series, across 15 ohms. There's 2 amps of current. And now we can do a little analysis with this circuit with initially all the current going this way. There is no voltage drop across this resistor. But at time infinity, now with 2 amps flowing through this resistor, there's a 10 volt drop across the resistor. Therefore, by Kirchhoff's law, there must be a 10 volt drop across this capacitor, and then you can solve for the charge that's stored. So you're not going to get all of the 30 volt drop across here just because there's a path for current to follow at infinity. So you're actually going to be, it's just Q will be the product of the capacitance and the voltage, so there'll be 2 coulombs of charge built up on that capacitor. So that's fairly simple when you apply the principle that a uncharged capacitor conducts and just acts like a wire, and therefore this is essentially shorting out this resistor. All the current will flow this way, and then at time infinity, that charge capacitor will totally block the flow of charge down this branch, but there will still be flow this way, and therefore a potential difference can be found just using the principles of circuit analysis. Okay, so that's 0 and infinity. Well, what about in between times? Well, we're going to have to do a derivation here, but we know that it's going to, say for this discharging circuit, that all the values of current and voltage and charge are going to start off at some value, and then they're going to drop down to 0, right, as the capacitor depletes. And this is foreshadowing here. It's an exponential decay curve. So, yeah, I'll just say this is current, but all of them will have similar graphs. We can put values on the graph, I suppose. So with this thing charged up, you can see it's charged up to 20 volts. So the time 0 quantities can be found. So the current in this circuit will just be V over R. That's 20 volts across a 10 ohm resistor. So it's going to start at 2 amps. Resistor voltage will be equal to capacitor voltage by the Kirchhoff law. And we can figure out, well, the charge is given there, isn't it? No, it'll be CV, because capacitance is charge stored for a given voltage. Q is CV. And so we've got a 10 microfarad charged to 20 volts. So that's 200 micros, and then a farad times a volt is a coulomb. So for our current graph, we can say it starts at 2 amps and it drops down to 0. And then I suppose we could do one more, right? The resistor voltage and capacitor voltage versus time are going to start off at this 20 volt initial value, and then they're going to drop down to 0. So I'm claiming that these quantities are exponential decays. We'll prove that in class. And as an exponential decay, it's going to have the form of some initial value times an exponential, negative exponential, because it's decaying, and that's the variable t. And then there'll be something called a time constant, which we use a capital T for. Whoa, that's messy. Hold on a sec. Let me fix that up. Okay, so yes, so our current will have the form a constant, the initial current, times a decaying exponential e to the minus t over capital T, where capital T is the time constant. Now we're going to show in a derivation in class that the time constant will use capital T. You could also use a Greek letter tau if you like. Tau. We're going to prove in class that this is actually equal to the product of the resistance and the capacitance, R times C. So a derivation of that will follow, but let's just use that idea then and do one more example together. All right, so here we have a capacitor that's charged up to 30 volts. Okay, so we'll draw the capacitor, and it's already charged up. And it's connected to a resistor, a 20 ohm resistor, like this. Sorry, that's not a very good wire. I'll fix that up in a sec. And it's half a farad. That's a massive capacitor. And it's charged to 30 volts, and here we have a 20 ohm resistor. Now, knowing that our quantities for this decay, for this discharging capacitor, will all be exponential decay, and will all have the form some initial value times a negative exponent. Now, I've written this equation for current, but the same equation would hold true for charge on the capacitor, for resistor voltage, and for capacitor voltage. So pause the video and then try answering this series of questions, and I'll go through the answers with you in just a sec. So pause now and give it a try. Okay, so let's see how you did. So here we had a charged capacitor, and it was charged to 30 volts. So it's going to discharge through the resistor, and the initial current is just 30 volts over the 20 ohm resistor. So that would be 1.5 amps of initial current. The time constant for this circuit is the product of resistor and capacitor. So that's 20 ohms times 0.5 farads is 10. And we'll show in class that a resistance times a capacitance does indeed have units of seconds. So we can write an equation then for current as a function of time. It's the initial current, 1.5 amps, times a decaying exponential minus t is a variable, over the time constant, which is 10. So that's an equation for current as a function of time. Now, the resistor and capacitor voltages are going to be the same in the circuit, and they're going to equal the initial value times the same decaying exponential. The only thing is that the initial value of both capacitor and resistor voltage is 30 volts. So VC will equal 30 volts times the same decaying exponential function, and both of these will be nice decaying exponential graphs for a discharging circuit. Now we're asked at 10 seconds to evaluate the current and voltages, so that means we just put in 10 here for the time, and then you can calculate everything. So putting in 10 for t, we can see that the 10s just cancel, and you're going to get e to the power of minus 1. And so 15 times e to the minus 1 is 0.552 amps. Now, to find the capacitor and resistor voltages, you could use this equation and put in 10 seconds for time and calculate that, but Ohm's law is still true, so that V is still IR, so we just found this current of 0.552 amps. So we could multiply that by the resistance and then get the resistor voltage in this way, and we know the capacitor voltage will have to be the same thing, so that's 11.04 volts. The last task in this example was to say, okay, well, this is 11 volts of resistor voltage. At what point would the voltage have dropped to its half value of 15 volts? So we use the exponential decay equation for resistor voltage, and then we just put in 15 for the resistor voltage, and then it's a matter of solving. So we would first divide both sides by 30, so that would just give us a factor of a half on this side, and then to undo the exponential function, we would just take the natural log of both sides to try and solve for t. Now this is ln 1 minus ln 2, and ln 1 is 0, so this side is just negative ln 2, and then ln undoes the exponential function, so this side is just minus t over 10. Cross multiply the negative 10, and t is 10 times ln 2 is 6.93 seconds, which, as expected, is less than the 10 seconds of the previous part of the example. So that's how to handle a decaying capacitor, decaying RC circuit and a review of the mathematics. So in class, we're going to do our derivation and prove that the time constant is indeed RC. Check the units, okay, to make sure that that really is seconds. And then we're going to look at a charging circuit again to try and come up with the equations for that. Now, in the charging circuit case, we're going to see that not everything is decaying exponentially because, of course, the capacitor is building up charge. So the graph and the equation will look slightly different. More on that in class.